You're welcome once again to our physics lesson. Today we are going to be talking about work, energy, and power, a very important topic in physics, very common also. So we are going to each talk about work, then energy, then power. We're going to take our time in turn to talk about each one of them. So what is work? In physics, work is said to be done only when a force moves an object in its direction. Anytime a force moves an object in its direction, we'll say that the work is done. That means before there can be work, there must be the application of a force, and that force must move an object in its direction. So work is more appropriately referred to as the product of the force and the distance moved in the direction of the force. If you have an object, if a force of F is applied on that object, and that force moves that object through a particular distance, then we will say that the work has been done. And that work can be obtained by multiplying the force and the distance that is moved in its direction. So we'll multiply force, which is in Newton, by distance, which is in meters, so that we'll get work that is in Newton times meters. And Newton meter is represented as joules, also means the same thing as joules. So the unit of work done is joules. Now, work is only done from what I've explained when you have a force and you have a distance. If either of them is zero, then there's no work. If, for example, an object just starts to move without any force moving it, that is miraculous. So there's no work done in physics in that case. But if there's the application of a force and that force has not been able to move the object, in that case, it means the distance covered by the object is zero. So we can assume that that work is being, the application of that force is not resulting into anything that can lead to work. So it means that the work done in that case is zero. Before work can be done in physics, there must be the application of a force in a direction. You can move an object, and once the object starts to move in the direction in which you are moving it, then we say that work has been done. You can decide to climb a stair. If you are climbing a stair, you are exerting a force on your tendons, muscles to go up, and you are also moving in that direction by moving up. So it is definite, it is necessary for us to have force and distance anytime we are to have work. And the unit of work is joules. Work can be positive. It can take up positive values if that direction is if the distance is in the direction of the force. In that case, we are so sure that it is that force that is bringing about the movement of that object in that direction. So work can also be zero. I just told you what can make work to be zero. Work can be zero if there's an application of a force, but there's no distance moved in that direction. So we'll say that the work is zero. But work can also be negative. How can work be negative? If there's an application of a force and the object is now moving in the reverse, you're applying a force on an object to move to the left, and the object is now moving in the reverse. It means there's another force that is actually necessary, that is actually in the picture, that is bringing the object opposite to you. So in that case, we can say that the work that your force is doing, because the object is moving in the opposite distance, is negative. So what can be positive, can be zero, can be negative. I hope we are going to get an example that we are going to use to treat and show that work can actually take up values from positive to zero to negative. So work, that is basically what we need to talk about. There are instances also where the force will be inclined. I told you when we were treating scalars and vector, that scalars and vector is one very important topic that finds a way to creep into all other topics. So in one of such applications where we can use vectors in work, we can actually have a force that is inclined. Of course, it is possible for you to attach a rope to an object and move it in this direction while the object moves on the floor. If the object now decides to cover a particular distance on the ground, let us say that the distance covered by that object on the ground is D, and the force is applied in this direction. Let us assume that the force is applied, the force F is applied at an angle of theta to the horizontal. What that simply means is, when you check very well, you see that this distance in which this object is moving is not exactly in the same direction as the force. So some students might want to say that there is no work done because the distance and the force are not in the same direction. That is almost true. But for the fact that I told you that anytime a force is inclined, we can actually resolve it. When we resolve it, it is now possible to find a force that is in the direction of that force, that is in the direction of that distance. If we resolve, remember what we always do, we will draw two components. There's a component that is horizontal and there will be another one that is vertical. The component that is horizontal will be F cos theta, because I told you the component beside the angle is cos, while the other component is sine. So this will be F sine theta. If we have this, then we can find the work now. We can see that there is a force and there's a particular distance that is in the direction of that force. Of course, if I resolve, I don't need that force anymore. I can easily clean it out and remove it from the picture. If that is done, I can now see that of the two forces that I've been able to get, one is in the direction of the distance. So I can say that the work is force. The force in this case will be F cos theta multiplied by the distance, which is D. Good. Now, that should be FD cos theta. The answer now is, what about F sine theta? Will F sine theta not have any work? Will it not create any work in this instance? To properly understand that, I want you to look at a situation where the force and the distance are completely perpendicular to each other. If the force and the distance are perpendicular to each other, let's say this is the force and this is the distance that has been moved. Anytime the two of them are at 90 degrees, anytime the two of them are at 90 degrees, the work will be 0. How did I get that? If we say that work is FD cos theta, one thing that can make the whole of this expression to be equal to 0 is if this theta is 90. If you put theta to be 90, you have FD cos 90. No matter what the magnitude of F or D can ever be, once you multiply it by cos 90, which is 0, I expect you to know that the multiplication will also be 0. So the whole of the work will be equal to 0. So if that is so, it means that anytime the force and the distance are at 90 degrees to each other, anytime the force and the distance are at 90 degrees to each other, then the work done will be 0. So therefore, I can use that to say that F sine theta in this case will not have any work done. If the distance that this object is moving is here, and if this is F sine theta will not have any work done because it is perpendicular to the distance. Anytime your force is perpendicular to the distance, it is not that force that is producing any work. So work is force times distance. I need to tell you also that work is a scalar quantity, despite the fact that it can take up positive 0 and negative values. It doesn't mean that it is a vector quantity. It is a scalar quantity. Work is a scalar quantity. In fact, all the three quantities that we are going to be treating in this topic are all scalar quantities. So that is that. A situation where an object has a force that is exerted on it and the object moves in the opposite direction, and the object moves in this direction. If you need to get the force, the work that is done, anytime a force is inclined to the distance or the distance is inclined to the force, you can use the formula that we already have. That is the force multiplied by the distance cos the angle between the distance and the force. You can always use that to get the value of the work. If I need to do this, I will multiply the force by the distance by cos theta. The cos of this angle, from this diagram, I can say that the angle involved here has to be an acute an obtuse angle that is more than 90. If we put 120, let us assume we use 120. By the time we put 120 into this expression, cos 120 is minus 0.5. We are going to have something that looks like minus 0.5 FD. So definitely, if you have, there are instances where you can get a negative work. Such is possible anytime you have an obtuse angle between the direction of the force and that of the distance that is given to you. So we can always use that to get whatever it is that we need. When you generalize FD cos theta, you can always use it to get the work, regardless of whatever angle you have been given. Where both force and distance are in the same direction. Where the force and the distance are in the same direction, I hope you know that when things are in the same direction, the angle involved is 0. So we can easily, if we use our work is equal to FD cos theta, we will discover that when we put 0, it will be F times D cos 0, which is 1. So the work in this case will directly be what we started with. That is force times distance. You are not using any angle because they are in the same direction. So you just multiply the force and the distance. We are going to see later the examples that we can use to further exemplify all of this to make them simple. Now, we'll look at energy. Energy is the capacity that you have to do work. Energy is the capacity that you have to do work. Energy is, if I ask you to go and run an errand for me, definitely there must be an energy that you are going to use to do that. If you have not eaten for the past 10 days, for example, such that you are so weak and you are lying on the ground, it is almost impossible for me to give you work to do and for you to be able to do it successfully, because you need energy that will come from food before you can now be asked to go on any errand, before you can do any work. Even work that is as simple as just standing up and running from a point to another, you will not be able to do it if you don't have any energy that you can use to accomplish that task. So energy is the capacity that we have to do the work that we have been sent. Of course, energy can come in various forms. We have different forms of energy. There are things that must be fed food. Humans must be fed food before they can do their daily work. We cannot be given electrical energy. It's not possible for you to plug humans. But there are several other objects that before they can do the work that you need them to do, you need to give them electrical energy by plugging them to the mains. So there are several forms of energy. There are several forms that we can use to get the capacity that we can now use to do work. One very good example, all of these things are classified together as forms of energy, and we have so many of them. There's chemical energy, the energy that we get from food, the energy that we get from chemical reactions, the energy that we get from burning objects, the energy that we get from combustion, the energy that anytime things react, they definitely give off chemical energy that can be used for some other energy. Now we have electrical energy. Anytime an object uses electricity or electric current, energy that has to do with the use of electric current is electrical energy. There are more. There's light energy, the one that comes from photons of light. There's heat energy, the ones that comes from the presence of infrared radiations. There is mechanical energy, the ones that has to do with machines and systems. Mechanical energy is usually divided into two. We have potential energy and kinetic energy. We are still going to come to that. There's sound energy, the energy that comes from speech or object from loudspeakers. We have sound energy. We have solar energy, the energy that comes directly from the sun. And we have geothermal energy. We have even newer forms of energy that have been discovered every day. We have nuclear energy, the energy that comes from the nucleus of atoms that can be harnessed to produce other forms of energy. Of course, it is possible for us to convert one form of energy to another. So there are so many forms of energy, and each form of energy has a formula that we can use to calculate them. But generally, please understand that energy gives us the capacity to do work. When you have energy, you can do an equivalent amount of work. If I have 10 joules of energy, I can do work that is equal to 10 joules. And once I do the work that is equal to 10 joules, I must have exhausted all of the energy that I've been given, and I'll go back to the same state just before I was given that energy. Now, we have different forms of energy, like I said, and they have formulas for calculating them. But specifically, we are going to look at mechanical energy. I said it earlier. There is a particular law that helps us to understand that energy can be transformed from one form to another. There's a law, it states that it's called the conservation of energy, and it states that energy can neither be created nor destroyed, but can be transformed from one form to another in a closed system. That means if you have a certain amount of energy, let's say 100 joules at the start of a process, at the end of that process, you are expected to have that same 100 joules. It's not possible for you to reduce or to waste the amount of energy that you have. What always happens is that energy will be transformed into some other forms, though those other forms might not be the useful form in which you want those energy to be. For example, a fan easily converts electrical energy to mechanical energy by moving. The question is, by the time you give it 100 joules of electrical energy, it's expected to give you that same amount as mechanical energy by rotating. But what always happens is, because we are still going to see that later on in machine, what always happens is because of the frictions involved in the moving part of most machines, the energy conversion process from one form to another is not always perfect. We have the energy being converted to other forms that are not desired. For example, when the fan works for a long period of time, you touch the body of the fan, you discover that it is getting hot. That heat is definitely coming from the electrical energy that you have supplied to it, that you expect it to use to convert to mechanical energy. So energy in a closed system, in a closed or isolated system, energy can neither be created, you cannot add to the amount of energy that you have all by yourself, or destroyed. You cannot just reduce the amount of energy that you have all by yourself, but you can convert the energy that you have at the initial state to another forms of energy. So in a closed system, energy can neither be created nor destroyed, but can be transformed from one form to another. That is the statement of the conservation of energy. Specifically, we are trying to look at the conversion of mechanical energy. Mechanical energy has two forms. We have the kinetic energy and we have the potential energy. The kinetic energy mechanical energy can be converted into kinetic energy, can be broken down into kinetic energy and potential energy. Now, mechanical energy can be divided into kinetic and potential energy. The formula for finding the potential energy is mgh. I'm going to come to that. While the formula that we use to find the kinetic energy is half mv squared. We are also going to still come back to that. Potential energy is the energy associated with an object by virtue of its position. Potential energy is the energy that an object has by virtue of its position in space. If I raise this marker to any point such that it's now having a specified height above the ground, then it's having kinetic potential energy. When an object is at any point in space, even if you place it on the chair, it's having potential energy. That potential energy you realize is having, and when you remove that chair, the object will fall with the whole of its energy. So anytime an object has a position, it is having potential energy. Anytime an object is moving, is on motion, it is having kinetic energy. So kinetic energy is the energy associated with an object by virtue of its motion. If an object is moving very fast, then it will have a very high velocity. Then we expect its kinetic energy to be very high. That is why kinetic energy is determined from velocity, because the moment you start to move, you now have a velocity. So definitely you have kinetic energy. The moment you raise an object above a particular height, it will have h, and that h can be used to determine its potential energy. So it is possible for an object to have both kinetic and potential at the same time. It is also possible that an object will have only potential. It is also possible that an object will have only kinetic. What we know is anytime you see a moving object, like a moving car, a moving bicycle, even a moving human, running human, what you are so sure that those objects have is kinetic energy. The moment you start to move, you have kinetic energy. And the moment you have a height above the ground, you have potential energy. So that is that. Now, there are instances where we can be given problems on the two to solve. If, for example, an object is raised from a particular height, let us assume that an object is kept on the top of a tower. The tower has a height. All of its energy, while it is at rest at that point, rests as potential energy. It's having potential energy. Let us assume that the potential energy of the object as it is 100 joules based on the height that it has and the mass and the acceleration due to gravity. By the time it starts to fall, by the time this object starts to fall, its height will gradually reduce because height is measured from the ground. Its height will gradually reduce. When its height reduces, its potential energy will also reduce. What it loses in potential energy, it is going to gain it in kinetic energy. As the potential energy reduces, the kinetic energy increases. Mind you, at this point, when it was just resting on the top of the tower, the kinetic energy is 0. It was resting, meaning it was not moving. And because it was not moving, its velocity will be 0. And because its velocity is 0, its kinetic energy will be 0, while resting on the top of this tower in space. But by the time it starts to drop, its potential energy will reduce. If it gets to this point, let us assume that at this point, the potential energy now reduces to 80. So definitely it has lost 20 out of the potential energy. It means the kinetic energy will now be 20 because it is now in motion. If it continues to fall further and its potential energy becomes 60 at some other point, it means its kinetic energy will be equal to 40. If it continues to fall and its potential energy becomes 40, it means its kinetic energy becomes 60. If it falls to a position where its potential energy becomes 20, its kinetic energy becomes 80. If it is about to touch the ground, when it's about to touch the ground, the potential energy becomes 0. Because at that point, the height is 0, so the kinetic energy is what it will have as its maximum, 100 joules. So what this chart is showing us is, at any point, when you look for the total energy, it's still 100 joules. When you add 100 to 0, is 100. When you add 80 to 20, is 100. When you add 60 to 40, is 100. When you add 40 to 60, is 100. So while the total energy remains the same, the energy is being transported between kinetic and potential. So this further helps us to confirm the law of conservation of energy, which states that the total energy is always conserved, though it can be transformed from one form to another. The total energy in this case is 100. We started with an energy of 100, and all through the motion, at every single point, the energy remains 100, though it is distributing itself in different ratio between kinetic and potential. Even at the point of touching the ground, at the point it's about to touch the ground, it's still 100. At the point it touches the ground, of course, both of them will reduce to 0 because the energy will now have to be converted to other forms like sound. The moment you throw an object down, you can hear it. You can hear the fall. The moment you hear the fall, it means the energy has now been completely converted into sound majorly, and some part of it can still be converted to heat. And the amount of sound energy that is also going to be produced will be 100 joules, to further confirm the fact that the total energy remains the same all through, though it can distribute itself between kinetic and potential. We are still going to see this in one or two examples that we are going to solve later on. Now, there are so many types of energy. There are so many sources of energy. Some forms of energy can be referred to as being renewable, while some other forms can be referred to as being non-renewable. When energy values are renewable, what that simply means is that we can reuse them if they are renewable. They cannot be completely exhausted. And those are very good. There are so many examples for renewable source of energy. The sun, for example, is a renewable source of energy. Hydroelectric Hydroelectricity is a renewable form of energy. Wind is a renewable form of energy. There's no way you can completely exhaust wind power or wind energy. It's not possible. So, but there are some sources of energy that once you have them, you can completely use them. For example, chemical energy that comes from food or burning item can be completely exhausted. Anything that can burn or that can completely react can actually be exhausted. Fossil fuels are sources of energy, chemical energy particularly, that can be completely exhausted. So they are non-renewable. When you exhaust them, it is not possible for you to reverse the process and recreate them. It is not possible for you to use them and reuse them. So they are non-renewable. So things like fossil fuel, things like food, things like chemicals are non-renewable, while things like wind power are renewable, things like solar energy are renewable, or their sources are also renewable. Now, we move on to power. Power is the rate of work done. Power is the rate of doing work. Power is also the rate of energy consumption. I must tell you something before we move on straight into power. Energy and work are interchangeable. Energy and work are interchangeable. That is why they even appear in each other's definition. When I was defining energy, I said energy is the capacity to do work. You give energy to a person, the person can actually do an equivalent amount of work. That is why there are instances where they can ask us to find energy, and we'll be given what can give us work. If that is given, we'll find the work and call it energy, because work and energy are interchangeable. There are times you'll be asked to find work, and we'll be giving what can get you energy. You find that energy and call it work, because work and energy are interchangeable. The work that you can do is equal in most cases to the energy that you have to do that work. Power now is the rate of work done. I can define it as the rate of doing work. I can also define it as the rate of energy consumption. Because when you have energy, that is what you are going to use to do work. And since we have said the energy that you have will help us know the equivalent amount of work that you can do. So the rate at which energy is being consumed so that work can be done. When you work on a system, its energy will increase. When you expend energy, it will lead to work done in a system. So the rate of energy consumption or the rate of work done can be called power. Yes, we can do work. We can all do work. If you ask me to run from here to the gate, I can do that. If you ask another person to do that same work, the person will do it. Both of us will have done the same amount of work. The only problem now is we will have done it in different times. Somebody will definitely do it faster or ahead of the other person. In that case, power is what helps us to bring the time component into the work that we do. Are you a person that can do a work of 100 joules in just 2 seconds? Do you have another person that can do that same work, 100 joules, in 20 seconds? In both cases, they are doing the same work, but obviously, they are not using the same power. This person's work is power, this person's power, if I have to calculate it, is work all over time. In that case, it will be 100 divided by 2, and that is 50. This other person is 100 all over 20, and 100 all over 20 is 5 watts. Here we have 100 all over 2, which is 50 watts. So this person that can do 100 joules within a short work of 100 joules within a short period of time definitely has a greater power than the person that will do the same work within a longer period of time. That person has definitely less power. So when we have this, the greater the power of an object, the less the time it will take for it to do the work. So the greater the power, the less the time it will be required for the object to complete that task. The less the power, the more the time it will take for the object to complete that task. So power is what helps us to bring time into the work and energy equation. Power is work all over time, as I've said. You can use work to calculate it. You can also use energy expended to calculate it, the energy consumed. The unit of power is the unit of work or energy, joules. divided by the unit of time, and the unit of time in this case is seconds. If you divide the two, you have joules per seconds, and joules per seconds means the same thing as watts. As I've said earlier, power is measured in watts, and it is a scalar quantity. It does not have direction. So that is all about that. We'll continue with machine under this topic, machines. Machines are devices that help us to accomplish a task better, easier, and quicker. So machine is a device by means of which work can easily be done. Machine is a device that allows us to do our work easily and more efficiently. So there are so many examples of a machine, and most items that you have around you probably falls into that category of being called a machine, because there's definitely something they are doing for you. Whatever you need to get to buy almost fall into the category of what you can call a machine. Now, there are so many types of machines. There's so many types of machines. We have what we call simple machines. We have what is called compound machine, and we have what is called complex machines. Simple machines are those ones that have only one features, and when you combine two simple machines together, we have what is called a compound machine. When we have more than two simple machines embedded in one, we have a complex machine. For example, most machines that we have around are actually complex. A motor car is a complex machine. It has so many simple machines that makes up its parts. The same thing for something even as small as a bicycle is a simple machine. But we are going to look at simple machines for now. And the examples of such include a lever. It includes what we call a wheel, an axle. It also includes what is called a screw jack. We have a pulley system. We have an inclined plane. And we have a gear wheel. So we are going to talk about a lever. A lever generally has the representation of the application of a load and an effort at the other end. If you are going to carry an object, any object, you will definitely need to apply a force. Of course, the object that you want to carry with that machine becomes the load. All the time is a particular force that the machine is expected to help you overcome. That force that the machine is expected to help you overcome is your load. There must now be a force that you must give to the machine. All machines cannot work on their own. That is why they are machines and they are not humans. It's only humans that can work on their own intuition. Machine cannot do such. For machine, you must give it something before it can now respond by helping you to do some other tasks that you have sent it. Now, for a lever, there's an application of a force. You must apply a force on a lever. When you apply a force on it, then the machine can now help you to overcome another force that you have placed, probably at the other end of the machine. The force that you want the machine to overcome for you is called the load. And almost all machines will have the load. Then the force that you give to a machine is called the effort. The force that you give to a machine is called effort. Both of them are forces, so they are represented in Newton. Now, the point of connection between the two is called the fulcrum. When we have a machine that has the fulcrum at the middle, if we have a machine that has a fulcrum at the middle, the fulcrum is between the load and the effort. We call this type of lever a class 1 lever, a first class lever. And there are so many examples. In fact, most simple machines that you have at home there are more first class levers than the other classes. So first class lever are those ones that have fulcrum at the middle. A very good example for you to consider is a scissors. If you hold the scissors, you know that you have to apply a force at one end while you will place the load at the other end. The load is going to help you. The load is what the blade of that scissors is going to help you cut through. So in using a scissors, you must apply a small force. That small force will now lead to a greater force that can be used to cut the load. The point of connection between the two is where the scissors has been screwed, the pair of scissors has been screwed. So clearly, the fulcrum is in the middle, the effort is at one end, while the load is at the other end. This is a class 1 lever. There's a class 2 lever. Class 2 lever are those ones that have load at the middle. They have load at the middle and probably effort at the other end. But what is more important in each of these class of levers is for you to know the one that is at the middle. If you know the one that is at the middle, then you can get the ones that are at the other points. Now, the load class 2, this is class 1 lever or first class lever. This is class 2 lever or second class lever. Now, since second class lever, a very good example is a wheelbarrow. If you have a wheelbarrow has a pan that you can use to heap the load that you are carrying. Of course, your effort will be applied at this other end where you are going to carry it, and the tire area, the wheel area, is where we consider as a fulcrum. So that is a second class lever. There's a third class lever. Class 3 lever are those ones that have the effort at the middle. The effort is at the middle. That means the fulcrum will be at one end while the load will be at the other end. So, and that is a class 3 lever. In a class 3 lever, all you just need to do is to understand that effort is at the middle. So generally, if I want to teaching you now, what I will expect that you do is that you know the acronym for class 1, class 2, class 3, considering those parts of those machines that are in the middle. In the first class, the fulcrum is at the middle, load is at the middle in the second class, effort is at the middle in the third class. So when you remember the word flare, you will know which is at the middle for each of this type of machine. Fulcrum is at the middle for class 1, load is at the middle for class 2, effort is at the middle for class 3. So that is that on that. So the lever will probably help us to describe a general thing that we can use to describe machines generally. Like I said earlier, for every machine, there are 3 things that you give to a machine. There are 3 things that we give to a machine, and we expect the machine to respond by giving us 3 things in return. Now, the 3 things that we give to a machine are, number 1, we give distance, we give a force, and because a force and distance are involved, we give work instead. Now, of course, when you consider a machine like a wheelbarrow that you use to pack heap of sand from one point to another, if you have to load, you have to put the sand in the pan. When you put the sand in the pan, the weight of the sand itself is the load. Then you will now exert your own effort in pushing it ahead. In pushing it ahead, you are moving, so you are moving your own effort. You are not just applying effort and staying at one point. You are applying effort and moving through a particular distance. The load too is a force that is exerted on that machine. And because you are moving, the load is also expected to also be moved. So both the load and your effort are moving in a particular direction. When you give a machine distance, you give it force, and you give it work, because force and distance are involved. the name of the force that you give to a machine, the name of the force that you give to a machine is called effort. I said that earlier. The name of the force that you expect the machine to respond with by helping you to carry or lift is the load. So while you give a machine your effort, while you exert your effort on the machine is expected to respond by helping you to lift the load. The distance that I will represent effort as E, and I will represent the load as L. The distance that you give to a machine will be called the distance moved by effort, while the load will move through its own distance. I will call that the distance moved by load. Now, of course, when you give a machine a force, and that force is moving through a particular distance, we expect that there will be work. The work done on the machine will be called the work done by effort. The work done on the machine will be called the work done by effort, while the work done by the machine will be called the work done by load. Most times, the work done on the machine will also be called the work done by effort. It can also be called the work input, because that is the work you are giving to the machine. So it has three different names that I've outlined. It can be called the work done by effort, it can be called the work input, it can be called the work done by the machine, the work done on the machine, the work done by effort, and the work input. Now, the work done by the machine is the work done by load, and it can also be called the work output. But most times, when you give machine work, when you give work to the machine, the work that you give to the machine is always more or at most equal to the work done by the work output. The work that you give to a machine will be more than the work that the machine will give to you. Why? Because number one, the machine itself cannot create work, because work is like energy, and we have said that work can neither be created nor destroyed. It is not possible for you to give machine work and you expect the machine to now respond with a greater work. It's not possible. If you give a machine 100 joules of work, expect something that is less than that 100 joules. Now, that means if I give machine a specific amount of work and I have an amount of work in return, can I say that if the work output is less than the work input, can I say that the work has been destroyed within the machine? If I give machine 100 joules of work and only 90 is coming out of the other end, can I say that that means that the machine can I say that the machine is destroying 10 joules out of the work that I have given to the machine? No. What I'm saying in essence is this: there are other things within the machine that will consume that work. Most importantly, there are frictions within the working part of the machine that will take away part of the work that you have given to the machine. So it simply means that when you give machine 100 joules and only 90 is coming out, it means 10 joules have been used by friction within the machine. They've been used to overcome friction within the machine. So this work output, this 90 joules output of work, will be regarded as the useful work output. Because 10 joules is also going to be an output, but it's not going to come out in the form that we're expecting, in the form that we desired. So it's going to, we can't say it is useless. Of course it is useless, but it is not coming out in the form that is required. So generally, there are three different types of work in the machine: the work that you are giving to the machine, the useful work that you are getting out of the machine, and the work done against friction. Let me just put that: the work done against friction, because it is friction within the machine that will not make the work output to be equal to the work input. You are giving 100, normally we should get 100. But because friction is taking out 10, is wasting 10 out of that, then only 90 is being obtained. So generally, when you are giving the work output and the work input, you can subtract them from each other to know how much work is wasted within the machine. You can subtract them to know how much work is wasted within the machine. And there's also something I need to tell you. Because work is force times distance, I can say that the work done by effort is equal to the effort multiplied by the distance moved by effort. I can also say that the work done by load is the force, that is the load, multiplied by the distance, which is the distance moved by load. Please always remember that too. And don't forget that the work done by load is the useful work output, while the work done by effort is the work input. So with all of this, you can easily find any of whatever it is that you need from here. We'll now move on again to more important parameters that we can use to describe a machine. We're just coming from a point where I said that machine is giving 3 different things, and we expect 3 things from the machine also. Now, all machines have mechanical advantage that can be used to measure how good they are. Mechanical advantage of a machine. The mechanical advantage of a machine can simply be expressed as the load of that machine, the load that machine is carrying all over the effort that can be used to carry that load. So when you divide load by the effort, then you are talking about the mechanical advantage of a machine. The unit of load, because load is a force, is Newton. The unit of effort is Newton. So both of them will cancel out. That means mechanical advantage is just a number, it has no units. The same thing for, mechanical advantage can also be referred to as the force ratio of a machine, because you are dividing 2 forces by each other. So mechanical advantage can also be referred to as the force ratio. So when we mention force ratio in a machine, we're also talking about the mechanical advantage, and it has no unit, as I've said earlier. Another important parameter that can be used to describe a machine is the velocity ratio. The velocity ratio of a machine is the distance moved by effort divided by the distance moved by load. The distance moved by effort of that machine divided by the distance moved by load on the machine. Once again, too, both distances are to be expressed in the same units, either meters and meters or centimeters and centimeters. When you divide them in those units, in their similar units, they will cancel out and they will have no unit left. So velocity ratio, just as mechanical advantage, both of them are dimensionless. They don't have units. The formula for the velocity ratio can also be called the speed ratio of a machine. Don't forget, can also be called the speed ratio of a machine. So if you are given the speed ratio of a machine, know fully well that you are looking for the velocity ratio. Now, there is now the most important parameter that can be used to describe how good a machine is. How good a machine is, that is the efficiency of a machine. The efficiency of a machine, must be the mechanical advantage or the force ratio divided by the velocity ratio multiplied by 100/1. Meanwhile, I must tell you that this 100/1 is not so compulsory. Efficiency of a machine can also be expressed in fraction. We can have the efficiency of a machine just being mechanical advantage all over velocity ratio. It can be expressed in fraction, it can be left in fraction, it can be expressed in percentage. In that case, you are multiplying by 100 and you are dividing by 1. So when you know the mechanical advantage, you use it. When you know the velocity ratio, you use it. So the higher the mechanical advantage, of course, the higher the efficiency of the machine. The lower the velocity ratio, the higher the efficiency. So higher mechanical advantage suggests a greater efficiency. Lower velocity ratio also suggests a greater efficiency, because efficiency and velocity ratio are inverse to each other. Now I can try to work on this equation to see other formulas that can be used to determine the efficiency of a machine. You will agree with me that we said earlier that mechanical advantage is load all over effort, and we also said that the velocity ratio must be the distance moved by effort all over the distance moved by load. If we decide to put these two expressions inside the efficiency formula, we will discover that the efficiency must be equal to mechanical advantage, which is load all over effort, divided by the velocity ratio, which is the distance moved by effort, all over the distance moved by load, times 100 all over 1. If that is the case, we can continue to work on this equation. We have load all over effort multiplied by the distance moved by effort all over the distance moved by load times 100 all over 1. If that is also the case, okay, this is still division. We are still dividing. So the efficiency must be equal to the load all over effort multiplied by, if we reverse this, distance moved by load all over distance moved by effort times 100 all over 1. So the efficiency must be equal to load times distance moved by load, the numerators, effort times distance moved by effort, the denominators, times 100 all over 1. If that is also the case, I can say that the efficiency must be, mind you, earlier on we were talking about this. We said when you multiply the load by the distance moved by load, you have the work done by load. When you multiply the effort by the distance moved by effort, you get the work done by effort times 100 all over 1. So efficiency can also be determined from the work done by load divided by the work done by effort times 100 over 1. Or more appropriately, we can express it as, remember I said that the work done by load is the work done by the machine or the useful work output. The work output, the useful work output, all over the work done by effort will be the work input multiplied by 100 all over 1. So either of these formulas can be used to determine the efficiency of a machine. Now we are going to be looking at each of these machines. We are going to try to see how they look like. And one thing that they all have is that there is a specific formula that can be used to find the velocity ratio of each. Yes, I've already given you the formula for velocity ratio. Velocity ratio of a machine is the distance moved by effort all over distance moved by load. That's a more general formula for all machines. But each of these machines, too, particularly from wheel and axle downward, have all specific formulas that can be used to determine their velocity ratio. For example, wheel and axle makes use of 2 cylinders. One is placed right inside another. Most of the time, wheel and axle is employed anytime you want to bring out water from a well. Then you have series of ropes, and there are ropes that are also joined to this end. So the rope on this are directly connected to the item that you are trying to bring out from the well. So the small cylinder here has a radius, the large cylinder here has a radius. The small cylinder, the large cylinder is the wheel, while the small cylinder is the axle. And it is the axle that the load is directly connected to, while the wheel is what your own effort is directly connected to. So the radius of the wheel, because the wheel is larger, the radius of the wheel I will use a big R, while the radius of the axle I will use a small r. The velocity ratio of the wheel and axle can be determined by doing the radius of the wheel divided by the radius of the axle. I don't even need to differentiate them using R and W, A and W. The big R stands for the radius of the wheel, and the small r stands for the radius of the axle. So that's the velocity ratio of a wheel and axle. Screw jack. Screw jack are those devices that you can use to lift up your vehicle anytime you need to perform maintenance work directly under it. Screw jack are those that you need to use to lift up your vehicle. Consists of a screw and it consists, the screw is directly connected to a handle that you can easily turn. So that's a screw jack. So you turn the handle. When you turn the handle, it raises the screw up by a pitch. What is a pitch? The curved pattern on a screw are called threads. A screw has it, all screw has it. The distance between a thread and another, that very small distance between one thread and another, is called a pitch. P, I'll represent it with P. Pitch is the distance between a thread and another. So when you turn the handle of this screw jack by one revolution, when it goes round by one revolution, then the screw moves up by a pitch. It moves up by a pitch. So if you want it to move up by 2 or 3 pitches, you have to turn it twice or thrice, depending on how you want it. You know, it still takes a lot of time before this will be able to get to the point where it can lift up your car, because the pitch is actually very small. You must have turned this several times. But the more this one goes around the revolution, the more you will be able to move the screw up by a pitch. So the velocity ratio here will be obtained from the load, the distance of the effort. Your effort is turning around a cycle. So the handle of this effort is usually referred to as the tummy bar. You can be given the length or the radius of the tummy bar. The length or the radius of the tummy bar is the radius that a full circle turn of the tummy bar will be able to go through. A full circle turn of the tummy bar will be able to go through. So the distance moved by effort should be 2 pi r or 2 pi l, depending on how you choose to call it, all over the distance moved by load. The load is connected to the jack itself. And we said anytime this goes through a turn, anytime your effort goes through a turn, the load goes up by a pitch. So it will be 2 pi r all over pitch. This is the formula for finding the velocity ratio of a screw jack. That's the formula for finding the velocity ratio of a screw jack. I hope you are taking note of each of these formulas, because ultimately these are the ones we are going to use to solve problems on a machine. Pulley system. Pulley system requires wheel, the use of wheel and ropes. They are usually used in construction sites to lift heavy machines. They are connected with strings. Most times, pulley systems are also referred to as block and tackle system. Block and tackle systems are pulley systems. So the velocity ratio of a block and tackle system is just the number of pulleys that you have within it. If I'm giving something like this, the number of pulleys that I have there, 1, 2, 3, 4, 5, becomes the velocity ratio. Now we move on to inclined plane. Inclined plane are commonly used to load heavy objects into very high platform. So we need to just move them through the inclined part of the plane into those platforms using a force, or of course generally we have people that will naturally always help us to push all of these objects up the inclined plane. One thing that inclined plane always have is the angle. Theta is the angle of inclination. Under friction, when we treat inclined plane, this angle is called the angle of inclination. Even now under machine, it's still called the angle of inclination. That angle of inclination will help us to get the velocity ratio of inclined plane. The formula for finding the velocity ratio of an inclined plane is 1 all over sine theta. Is 1 all over sine theta. That's 1 all over the sine of the angle of inclination. Then we'll move on to gear wheel. Gear wheel involves two intermeshing gears. Gears generally have tapered tooth on the edges. What we use gear for most times in machine is to transmit the motion from one object to another. So gear, such that when a gear rotates in a particular direction, because the teeth are connected, it is now possible for them to continue to transmit the motion to the other gear. There can even be up to a connection of up to 3, 4, 5 gears. So knowing fully well that when this rotates, the connected edges will help to drive the other parts too. So this will be called the driver gear, and that is the one that your effort is directly in contact with, because that's the one that will initiate the motion. This will be called the driven gear, because this is the one that is connected to our load. Now, the velocity ratio of gear wheel system will be the number of teeth on the driver gear all over the number of teeth on the driven gear. And this is just the velocity ratio, the formula for finding the velocity ratio of a gear wheel. Now, we are going to consider some questions now on work energy and power and machine. We are going to try to consider a whole lot of questions because there are so many aspects to the concept of work energy, power, and even machine. So two of the questions we are going to be starting with are what you have on the board. In the first case, we said the force versus displacement graph of a body is given by the quadrant of a cycle as shown above. What is the work done by the force in moving the body through a distance of 20 meters? In moving the body through a distance of 20 meters, what is the work done? Mind you, I told you in one of our previous classes that work, if a quantity can be obtained by the simple multiplication of two other quantities, then such that when one is plotted against the other, then that quantity that is their multiplication becomes the area. Area on a graph means multiplication in the formula. We know quite well that work is force times distance, which can also be referred to as displacement. So now, if you want me to find work in this diagram, all I need to know is work being the product of force and distance, and I have force and distance or displacement set out on the graph. Then all I need to do to get the work is just to find the area covered by this graph. And the question has told us that this is a quadrant. A quadrant is a quarter of a cycle. So to get the work, I will just find the area of the shape that I have here. And that should be, the area of a cycle is 1 over 4 pi r squared. The area of a quadrant is 1 over 4 pi r squared. So that becomes 1 all over 4 times pi, 22 all over 7. That's what the question gave us, multiplied by the radius. The radius, if this is a quadrant, this must be the center of the circle. And if that is the center of the circle, any line from the center to the circumference is the radius. So the radius, if you take this side, is 20. The radius, if you take this side, should be 20. If this is truly a quadrant, it has to, these two values here must be the same. So it means the radius is 20 times 20. So we can complete this by just getting our work done in joules. We can complete this by just getting our work done in joules. And I think the formula, that will give us 22 times 400 divided by 28. 314.285. 314.285 divided by 28. 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 0.285 joules, 286 joules. And that's the answer to this question. We move on to the next. We are told in the other question that the diagram above represents energy flow through a hydroelectric power. The efficiency of the energy conversion is what? What is the efficiency of the energy conversion? Let me help you make a sense of what has been drawn. In hydroelectric power, water comes with an amount of energy. That water is expected to drive a dam, and that dam is expected to take part of the energy to drive a turbine, which in turn will be used to drive an alternator that will generate electricity. So basically what we do in a dam is to take in water that is coming at a very high velocity, which is also high kinetic energy, which translates into high kinetic energy. Then we convert it to electrical energy. The much of the kinetic energy that we can convert to electrical energy will help us understand, will help us get the better of efficiency out of that system. So the water comes in with energy E1, and we are only able to extract electrical energy E3 from the process. It means the water is still now living with some of the energy that we ought to have extracted if the process has been very, very efficient. So now, remember that we said the efficiency of a machine is the useful work output all over the work input multiplied by 100/1. And I can use work and energy, I told you earlier, interchangeably. So that should be useful work output. The output that is useful is E3. The only input that we have in this problem is E1. They will multiply it by 100/1. That should be the efficiency in percentage. Remember I said that the efficiency can also be expressed in fraction. So the fractional efficiency must be equal to E3 all over E1 without the 100/1. So basically, that is how to solve this problem. We'll try to take more questions. Now, we are told that a bullet of mass 40 grams traveling at 300 meters per second strikes a target normally and penetrates a distance of 20 centimeters in the target before coming to rest. The average force exerted on the bullet by the target, will be equal to what? We have a bullet shot to meet a target normally. That means perpendicularly to the surface of the target. What are the other things that we are given? A bullet of mass 40 grams. The mass of the bullet is 40 grams. If we change that to kilogram, we divide by 1,000. The mass of the bullet will be 0.04 kilogram. Traveling at 300 meters per second. It's traveling at a velocity of 300 meters per second. 300 meters per second at a velocity of 300 meters per second. We are told that it strikes a target normally and penetrates a distance of 20 centimeters. It strikes a target and penetrates a distance of 20 centimeters within the target. It strikes a target and goes in, penetrating a distance of 20 centimeters in the target. If we decide to change that 20 centimeters, the distance, if we change it to meters, 20 centimeters divided by 100, we should have 0.2 meters. The question now is that we should find the average force exerted on the bullet by the target. As you shoot this object into the target, we expect you to understand that there will be a restrictive force that the target will use to eventually stop it. That force that the target is exerting on it, that the block is exerting on it, is what we have been asked to find. So here we'll just use a simple equation of energy and work. When you shoot the bullet, if a bullet is shot, it will process one form of energy that we call kinetic energy. I told you that kinetic energy is the energy associated with moving objects. Now you have, the object has a kinetic energy. By the time it gets to the target, what it will use that kinetic energy to do, remember that we said energy is what gives us the capacity to do work. It will use that kinetic energy to do the work. What's the work? The work is to penetrate into the target. So we'll simply say that to solve this question, we'll just say that the energy possessed by that bullet must be equal to the work done in the target. And simply we now know that the energy is kinetic energy, so that should be half mv squared must be equal to the work done. The work done must be force multiplied by the distance. So clearly this should give us the distance. If we make it the subject of the formula, okay, force is what we are looking for. This force is what we are looking for. That should be force must be equal to half mv squared all over the distance. And that should be half multiplied by the mass here is 0.04. The velocity here should be 300 squared, while the distance should be 0.2. I've represented it with S earlier, so we can determine that and we'll give out the expression as 0.04 times 300 squared divided by 0.4. The answer is 9,000 joules. The answer is 9,000 Newton, sorry. The answer is 9,000 Newton. Newton is a unit of force, not joules. So that is the answer to that question. Also, we take more questions. We are told again that 24 kilojoules of heat is produced by the combustion of a certain quantity of petrol in an engine rated 10 watts. That engine is rated 10 watts. If 1/4 of this heat is converted into mechanical energy, how long will the engine run for? 24 joules of heat is produced by the combustion of a certain quantity of petrol in an engine rated at 10 watts. If 1/4 of this heat is converted into the mechanical energy, how long will the engine run for? Number one, we have 24 joules of heat energy. Only 1/4 of this value was converted to mechanical energy in the engine. So the mechanical energy that we have must be equal to 1/4 of 24 kilojoules. And that should be 6 kilojoules, which is also 6,000 because kilo means 1,000 joules. Now we are told that the power of this engine for which this mechanical energy has been given is 10 watts. It's 10 watts. So how long will this engine run for? The engine will run for, remember that the power is equal to the rate of consumption of energy, and the energy that we want to consume is 6,000, not 24,000. The heat has given us the mechanical energy, and mechanical energy is what we are going to use to drive the engine. So that will be the energy, 6,000 joules, divided by the time, t. But the power has already been given, so I will do 10 is equal to 6,000 divided by time. It means the time must be equal to 6,000 all over 10, and that should give us 600 seconds. 600 seconds is the correct answer for this problem, and we can move on with the solution to more problems. Still under work, we are told that a force of 15√3 Newton is applied to a crate at 30 degrees to the horizontal surface, and it is used to drag the crate through a distance 7 meters along the surface. If the work done in dragging the crate is 175, what is the frictional force between the crate and the floor? What is the frictional force between the crate and the floor? We have the floor, we have a crate, then we have a force of 50√3 dragging a crate at an angle of 30 degrees. 30 degrees. We are told that this is the crate. We are also given the fact that, so now we can solve it. They said a force of 50 root 3 applied to a crate at 30 degrees. It is applied to a crate at 30 degrees as shown. It is used to drag the crate through a distance of 7 meters. That means the crate moved forward because it was dragged through a distance of 7 meters. To move forward through a distance of 7 meters. Now, along the surface, if the work done in dragging the crate is 175, the work done is 175 joules. Now, what is the frictional force between the crate and the floor? There's going to be a frictional force because the question said so. So if there's going to be a frictional force, we need to first know. You have to refer to our class on frictional force to know how to establish the direction of friction. But we need to know what's the direction of motion. If the crate is moving, it will have to, because we are told that the crate is dragged forward, so it is moving horizontally along the surface in this direction. We expect the friction to also be in this direction. I was telling you earlier that if a force is inclined, we can resolve it. When we resolve that force, we resolve it into both horizontal and vertical. We resolve that force into horizontal and vertical. If we do that, the horizontal component will be 50 root 3 cos 30, while the vertical component will be 50 root 3 sin 30. Please refer to our class on scalars and vector to know how to resolve a vector quantity as we have just done. Now, we have been given the work done. We can see that if we are to find the work, we said that the work must be force times distance. There are two forces along the direction of motion of that object. While 50 root 3 cos 30 is pushing it forward, there is a frictional force that is opposing that motion. In considering the force, we have to use the net force. The net force between 50 root 3 cos 30 and the friction. The net force, of course, will be 50 root 3 cos 30 minus the frictional force Fr. We cannot use 50 root 3 cos 30 alone. When you are doing the work, the force that you have to use is the net force. The net of 50 root 3 cos 30 and Fr, because those are the two that are along the direction in which the object is moving. While this is creating the positive work, this is creating the negative work. Remember I said that when the force is against the direction of movement, the work is negative. So if you are given a work, it has to be the net work that is obtained from the net force. So we cannot just use 50 root 3 alone. So we have to use 50 root 3 cos 30 minus the friction, multiplied by the distance, which is 7. The work in that case has been given to be 175. So we can completely evaluate this for the friction. So we'll say 50 root 3 cos 30 minus the friction must be equal to 175 divided by 7. 50 root 3 cos 30, if you express it in short form, is expected to give you root 3 all over 2 minus the friction is equal to 25. So if that is the case, root 3 times root 3 is 3. 3 times 50 is 150. 150 times divided by 2 is 75. 75 minus the friction must be equal to 25. If that is the case, we'll find friction by doing 75 minus 25. And 75 minus 25 is 50 Newton. It means there will be a frictional force of 50 Newton on this object. We'll get another question done. We are told here that a stone of mass 50 grams is projected vertically upward from the ground and it acquires a velocity of 12 meters per second at a height of 20 joules. The initial kinetic energy of the stone is, we have a stone, that stone has been projected vertically upwards. It has been projected vertically upward. Now, the stone is said to have a mass of 50 grams And we are told that it acquires a velocity of 12 at a height of 20. When it got to a height of 20, at that point that it got to a height of 20, it acquired a velocity of 12 meters per second. 12 meters per second. 12 meters per second at a height of 20. So at this point, when the height is 20 meters, its velocity became 12. The question now is that we should find the initial kinetic energy of the stone. The initial kinetic energy of the stone is the kinetic energy at the point where it was thrown up. That is this point. What is the kinetic energy at this point? It was thrown up, and when it got to a height of 20, it has a velocity of 12. So I can simply say that this is not its maximum point. When you throw an object up, at the maximum point, its velocity is expected to be 0. We are going to see that very soon. When the velocity is 0, the kinetic energy must also be 0. So at this point, its velocity is 12. It still has a value for velocity that is not 0. It still has a non-zero value for its velocity, so that cannot be the maximum height. So at that point, again, we are given the height. So what I think we should do is, at this point, since I know its velocity, I can find its kinetic energy at that point. Since I know its height, also at that point, I can find its potential energy. So let me try to do that. The kinetic energy at the point in question should be half mv squared. And that will be half multiplied by the m is the mass, and the mass of that object is 0.05 because it is 50 grams. So when we change it to kilogram, we have 0.05. The velocity is 12. We square it. We should have 0.05 times 12 squared divided by 2. And our answer should be 3.6 joules. 3.6 joules. We can also find the potential energy at that point. The potential energy's formula is mgh. Mgh is the mass is 0.05. Acceleration due to gravity 10 for this question. H is the height, and the height is 20. If I multiply all of these, I will have 10 times 20 times 0.05. This gives us 10 joules. That means at this point, the kinetic energy is 3.6, while its potential energy is 10 joules. If I add the two together, it means the total energy at that same point must be 13.6 joules. Total energy at that point is 13.6 joules because at that point it's having a kinetic energy of 3.6 and it's having a potential energy of 10 joules. When you check the distribution of energy between kinetic energy and potential energy that we discussed earlier, you will discover that I said that it is necessary for you to know that at the base, when you throw an object up, or when an object is falling, at the top it will have a potential energy which will represent the maximum potential energy. I assume that if the potential energy is 100, the kinetic energy will be 0. So as it's falling, the potential energy will gradually reduce while the kinetic energy will increase. Let's assume that the potential energy at this point is 30. It means the kinetic energy will be 70. When it is about to touch the ground, it will have a potential energy of 0 because there's no height on the ground, while the kinetic energy will now be 100. So the idea is at any point, the total energy must be equal to 100. The total energy must be equal to 100. The total energy must be equal to 100. If that is the case, there are two things I want you to see. Number one is that the total energy is always constant. Once you know it at a point, you know it at every other point. Number two, there are two values that are directly equal to the total energy. The potential energy at the top, the potential energy at the maximum height is equal to the total energy because the other form of energy at that point is 0. At the bottom too, the total energy, the kinetic energy is also equal to the total energy. Why? Because the other form of energy at that point, potential energy, is also 0. So the kinetic energy at the ground level and the potential energy at the maximum height are both equal to the total energy. So if they want me to find the kinetic energy at the bottom or the potential energy at the top, I don't really need to calculate it once I know the potential, once I know the total energy. And in this case, the total energy is 100. So that's the same thing I'm going to apply here. The total energy is 13.6. It won't change at any point. And at the bottom, I expect the kinetic energy to also be 13.6 joules, because the kinetic energy at the base, at the point of throw, at the point when it's still on the ground, must be equal to the total energy. So the answer to this question is 13.6 joules. We'll take one more question on machine, and we end the topic. The last question for today. We are told that the wheel and axle of a wheel and axle, the wheel and the axle of a wheel and axle have radii 50 centimeters and 10 centimeters respectively. If 1/5 of the work done by the effort is used to overcome friction, an effort of 500 Newton applied to the wheel will raise a load of what? We have the radius of the wheel, which we are going to represent as a capital letter, the radius of the axle, both of them are given to be 50 centimeters and 10 centimeters. We are also given the effort of 500 Newton. The effort is 500 Newton, 500 Newton. This question wants us to calculate the load. And one other information that we are given in the question is that 1/5 of the work done by the effort is used in overcoming the friction. I told you when we were talking about the 3 things that you give to a machine such that the machine will respond by giving you 3 other things. I said that we give a machine the work done by effort or the work input. The machine is to respond by giving you the work output or the work done by load. Then the difference between the two must be the work done against friction. The work done in overcoming friction is the difference between the two. If not for friction, the work input must be equal to the work output. The work done by effort is also the work input. Don't forget, the work done by load is also the work output. Good. So in this question, we are told that 1/5 of the work done by effort is used to overcome friction, is the work done to overcome friction. 1/5 of the work done by effort is used to overcome friction. If that is the case, it means if work done by effort is taken to be X, the work done against friction will be 1/5 of X. And since work done by effort is the only input, 1/5 is coming out as a work done against friction. It means the remaining will come out as a work done by load. The work done by load will now be 1 minus 1/5x. X minus x, the work done by effort, minus 1/5x, the work done against friction, and that should be 4/5x. If that is the case, we can now find the efficiency. The efficiency of the machine can be expressed as work done by load or useful work output all over work done by effort multiplied by 100 all over 1. Mind you, I expect you to know that the work done by load is 4/5x all over the work done by effort, which is x, multiplied by 100 all over 1. If that is the case, I cancel out the x, and you have an efficiency that is equal to 4/5 of 100, and 4/5 of 100 is 80%. 80%. If that is the case, then I know the efficiency. One other thing I can easily get from all of this combination is the velocity ratio. Earlier on, I gave you the formula for finding the velocity ratios of all the simple machines. Now, particularly for wheel and axle, the velocity ratio of a wheel and axle is the radius of the wheel all over radius of the axle, and that is 50 centimeters divided by 10 centimeters. If we divide 50 by 10, we should have 5. So the velocity ratio for this machine is 5. If the velocity ratio is 5, I can now rewrite the formula for efficiency. Efficiency can also be expressed as mechanical advantage all over velocity ratio multiplied by 100 all over 1. If that is the case, the efficiency, I've already obtained it to be 80. The mechanical advantage, I don't know. Let me represent the mechanical advantage as y. The velocity ratio must be 5 multiplied by 100 all over 1. If I continue with that 5 year 1, 5 year 20, it means 20y must be equal to 80. Y should be 80 divided by 20, and 80 divided by 20 is equal to 4. If 80 divided by 20 is equal to 4, then I can now do my mechanical advantage. I can express my mechanical advantage as load all over effort. My mechanical advantage is 4. My load is what I've been asked to get when an effort of 500 newtons is exerted. The load must now be 4 multiplied by 500 newton, and the answer should be 2000 newton. So how have I been able to solve this question? I've used the statement that they gave me for work to determine the efficiency. Once the work is expressed as a fraction or a percent, once any work is expressed as a fraction or percentage of any other, I can use that to get my efficiency. From the efficiency, from the information given, I was able to get the velocity ratio, and from the velocity ratio, I was able to find the mechanical advantage, which in turn gave me the load that will be lifted by an effort of 500 newton. With that, we have come to the end of work, energy, power, and machine. Thank you very much for listening. Join us for another interesting episode. Thank you.